Here is sample test 3, problem number 4. In the figure at t equals 0, the switch is closed with the capacitor uncharged. If C is 30 microfarads, EMF is 20 volts, and R is 4 kiloohms, how much energy is stored by the capacitor when the current is 1 milliamp? So we have ourselves an RC circuit with a capacitor of 30 microfarads and a EMF, a voltage of 20 volts. And R is 4,000 ohms. 4,000. And we have a switch. And we know that our current is going to be equal to our maximum current, e to the negative t over tau, where tau is the time constant. And our maximum current is going to be the voltage of the battery divided by the resistance, e to the negative t over tau. So that maximum current, which is E divided by R, epsilon divided by R, is 20 volts divided by 4,000 ohms, which will be 5 milliamps. So in general, since I is equal to our maximum current, E to the negative t over tau, then when the current is equal to 1 milliamp, we have 1 times 10 to the minus 3 is equal to 5 milliamps, e to the negative t over tau. So at that particular time, this is what occurs. The 10 to the minus 3's cancel out. 1 divided by 5 is 0.2, so we have 0.2 is equal to e to the negative t over tau at that particular time. Well, the voltage across the capacitor is equal to the voltage of the battery, 1 minus e to the negative t over tau. And we just figured out the negative t over tau for this situation. So this is going to be equal to 20 volts times 1 minus 0.2, 20 times 0.8. So the voltage across the capacitor is going to equal 16 volts. Nice to know, which means that the energy stored in the capacitor at that time, which is 1/2 CV squared, will be 1/2 times 30 microfarads times 16 volts squared, and that's going to be equal to 3,840 microjoules, which you could write as 3.84 millijoules. So that is the energy stored in the capacitor at that time. Here's an alternate way we could think about this problem, just a goofy way. If we know that the current is 1 milliamp, then we can figure out the voltage across the resistor at that time, because according to Ohm's law that should be I times R. So we have 1 milliamp, 10 to the minus 3, times 4 kiloohms, 4 times 10 to the 3. 10 to the 3 and 10 to the minus 3 cancel out. And so at that moment, the voltage across the resistor is 4 volts. Hence, the voltage across the capacitor, which is the EMF of the battery minus the voltage across the resistor, according to Kirchhoff's voltage rule, would be 20 minus 4, or 16 volts. So that's an alternate way, maybe just a unique way in this particular problem where we can kind of circumvent all the other stuff. Don't count on it, but it's just an easier way to do this particular problem. And hence the energy stored in the capacitor again would be 1/2 CV squared, 1/2 times 30 microfarads times 16 volts squared, 3,840 microjoules, or 3.84 millijoules. So that would be an alternate way to solve this problem. Energy stored in the capacitor, 3.84 millijoules, when the current is 1 milliamp.